Yes, before I start, I actually would like to talk a little bit about metro water recovery so you know who we are and the magnitude and the impact of things we do for the environment in general. Energy just being one of them and a growing field, as you will see. And then I want to specifically talk about thermal energy in wastewater and how that can be used, because there is not a lot of attention on that. Has anybody actually heard about recovering thermal energy from wastewater? Some of you, that is actually already great. Very impressive. And then I want to talk about the first projects that we have actually already in this area, and a large project we took on online about 3 years ago that you may have an opportunity to see. And just give you a broader perspective of what is happening with that type of energy internationally and nationally, because there's a lot of development right now, and it's just on the takeoff. And so you will come across that more in the coming years. Good. So let's get going. Metro Water Recovery, if you're not aware, is a wholesale provider for wastewater treatment, collection and treatment in the metro area. We were formed really decades ago. I just gave a presentation on Tuesday for the Beer Talks in Golden, where I gave a history of our district and organization. So it's been around since the 30s when we started to collect water, we started to treat it, and have now 2 large facilities in the metro area. The interesting thing, we were formed to protect the South Platte. The South Platte was a mess about 100 years ago. A lot of waste went into it, and Metro was formed. And really that is one of the prime reasons for us, is to protect the water quality in the South Platte River, which is used for many purposes. For fishing, if you're a fisherman, for drinking as a drinking water source downstream. And at times of the day, about 6 months of the year, we are most of the river. 85% of the water. You see actually the sandbanks just upstream of where we are discharging the water. So very important for the aquatic life and also for human uses of that water. We're serving right now about 2.2 million people and have many connectors. You see the map here. There's really just a few islands in the metro area that we are not serving. And consistently, people knock on our door and inquire about joining our infrastructure and collection, because it's starting for some smaller utilities to become cheaper to join our district and have water and biosolids being treated through us. We have a fair amount of interceptors. This will be important for later on. So over 200 miles of interceptor linear footage. And you will see in a little bit why this is important. Before I go there, I want to give you an overview of the environmental relevance and what we're actually doing. It may just be interesting for you what actually happens with your wastewater when it comes to our facilities. So the water that we're right now, our large facility at Metro that you may know if you're a bicyclist and you go down Clear Creek and then turn right on South Platte, you actually drive right by our facilities. You see them across the fence. We are treating on average 140 million gallons of water, which is recovered in several ways down in the South Platte, down actually to outside of our state in Nebraska. Very high interest in that water because of water rights and drinking water production. Otherwise, this water is used for agricultural, aquatic life, recreation, and as I said, a drinking water supply. There are several alluvial wells next to that river where that is reused again. We also recover the biosolids and have a very large farm area on the east side of Denver, about 50,000 acres, where the biosolids are, we are using bacteria to clean the water. The bacteria are very rich in nitrogen and phosphorus, but we have also water associated with that. And so that is a very high-class material, Class B biosolids that we bring onto the farmland. We have also many farmers on the east side of Denver that are interested in these biosolids. And so it's a recovery of nutrients for food production. We are producing large amounts of grain with that go for food production, are used for food production. We are also recovering phosphorus. All of us in our daily lives are putting phosphorus in trace amounts in the water, but we get about 7 milligrams per liter, which doesn't sound like a lot, but if you multiply it by 140 million gallons per day, we get a fair amount of phosphorus into our facility, and we are required to remove it. And so there is a connection with energy because it actually takes a lot of energy to produce artificial fertilizer. In our case, we are quite energy efficiently removing the phosphorus and are capturing it as what we call struvite. So that's a salt. It contains ammonium, phosphorus, and magnesium, everything that plants love. It's a slow-release fertilizer, and it looks like sand, but stuff grows really well on it. I tried it out on my office plant. And yeah, so we're recovering that. And Ag One, if you know that provider here, it's a composting provider here in our area, is using that and distributing it with compost. Let's talk about energy. Before I actually talk about thermal energy, I do want to make you aware that we have since decades produced energy in form of electricity and heat with biogas. Biogas is the gas that is produced in many wastewater facilities across the country. The biosolids that I told you about, so that's the biomass that we essentially need to stabilize. You can't take that organic and put it somewhere. It needs to be stabilized, and so we put that in large anaerobic digesters. This is nothing else than your composting bin in summer when the lid is closed, it doesn't get enough oxygen. We do that on purpose and very controlled, and so it creates biogas, and 60% in that biogas is actually methane. And that methane we're using in through cogen engines to produce electricity, and we're also using the heat on site for other purposes, primarily for heating the digesters. So that's quite an amount of heat and electricity equivalent to, we use that electricity right now on site. 60% is of the electricity that we are using is produced. We're using quite a lot of energy. We're paying about $6 million per year just for energy to run wastewater treatment plants. And that is a large facility that is relatively energy efficient compared to smaller scale facilities. But in equivalent, it could provide the power for about 4,000 homes. All right, let's finally get to thermal energy. We could produce, we don't yet, but we could produce up to 150 megawatts of energy. And that's what I want to talk about today, because we don't. And there we need to talk about this because the alternative of what we need to do with that thermal energy is not very appealing. I will show you in a second that we are, from regulations, required to remove that energy because it has impacts on aquatic life. I will show you that, and the track that we are on to meet that is a technology that we don't like because it's not sustainable. And we are sort of on a timeline to find something to do with that energy. And the options are good because the technology is there. We are not pioneers in using that amount of energy and that form of energy, but we got to act on it and create these opportunities. For comparison, the city of Vienna in Austria, so the capital of Austria, I had the opportunity to visit that facility, the very large wastewater treatment facility, actually very much comparable to the metro facility we have, is already using that, has the facility up and running, and is removing about 50 megawatt of energy from their wastewater and providing it into their district energy system, with a plan to expand that to 100 megawatt in the future. So this is already being done, and being done in areas where energy is much more expensive. So let's talk about wastewater thermal energy pathways and why are we talking about this topic and why is it even an issue? So all of you probably used hot shower run your dishwasher. We are all using hot water. Even if you go to the restroom here or in open areas, you just want to wash your hands, oftentimes hot water comes out. We don't even think about it. It seems pleasant, but it's starting to become an issue. That wastewater has always been going to wastewater treatment facilities, but now regulators and scientists have looked at the impact that we have in the metropolitan area on our streams and rivers. So our streams are coming from mountain areas. We are having cold water and warm water surface waters. And we have cold water fish, right? If you're a fisherman, you love to catch a trout in our waters. And with the heating that we are providing, even if it's small increases of heat, it has impact. It provides impacts on aquatic life. Specifically here, the regulator, CDPHE, is looking at certain indicator species, and jolly darter is a very small fish, probably as long as my finger. The irony is we don't even find this fish in the water, but it could be here, and it is an indicator fish for cold water aquatic life. And so the regulators are trying to protect that habitat and are setting standards for us to reduce the temperature in wastewater. And that's not just Metro. This is CRES, this is Fort Collins. You can go along the Front Range. We all have that problem in the larger urban areas, specifically in those where the amount of wastewater we put in streams is very large, and so the temperature impact is very high. So to illustrate the extent of that, I hope you can see that. Is that a pointer also, Tom? No, maybe not. But what you're seeing is sort of a cyclic curve. That is the temperature that is very typical for domestic wastewater in Colorado and in our climate. So in wintertime, the minimum is about 14 degrees Celsius. And in summertime, we're going up to about 22 degrees Celsius. So that's about the fluctuation, and it's very predictable. Overlaid on this are the temperature standards that we will need to be required actually in our facility, in the large facility in Metro in 2031. And then some of you may have seen on the map, I had another little star. We have a second treatment facility that is much smaller. That is also along the South Platte in Brighton. We call it the Northern Treatment Plant, and there we will already have to meet these requirements in 2026. It's smaller we're treating there right now about 7 MGD. So what you're seeing is it's quite interesting how regulators set these standards, but essentially in summertime, that's the plateau up on top. The standard is about 23 degrees. We don't have an issue with that yet. Our temperature is always lower than that, but you see once we get into wintertime, specifically on the 1st of December, that's when these standards are kicking in for everybody along the Front Range, and everybody is trying to figure out how do we cool the wastewater on the 1st of December. In our case, quite substantially, we need to remove about 7 to 8 degrees Celsius out of that water. So for the mechanical engineers and you working on HVAC, you can do quickly the math, 140 MGD. We need to pull out 7 degrees out of that water. That's quite an amount of heat that we have available. And what can we do with it? The current standard of the industry, if wastewater treatment facilities need to remove that air, are cooling towers. So that's nothing very special about these cooling towers. We use them in industrial sites all the time. It is a bit interesting to put wastewater on there. That is new because typically cooling towers are being used for quite clean water. So we actually have to figure out how does that work with wastewater. Even if it's cleaned, it still has residuals, small amounts of carbon that biomass, etc., can grow on. And so we've tested since about 2-3 years a pilot unit out at the Northern Treatment Plant just to see how does this even work. And it works, but we have some concerns with that. At a very large scale at our Metro facility in Denver, we don't have the space for these cooling towers. We have it now, but with all the other requirements that we know we need to put into place to treat the water in the future to higher standards, we're running out of space. We also are putting energy in, right? You have to pump the water up, and these are not shallow basins. We're talking about meters, 5-6 meters of head that we need to pump a large amount of water over. In average, we need to put in about 5-6% in addition to everything else we are right now, our energy consumption, which may not sound a lot to you, but what we're really trying as an industry is to become energy neutral. And so now we're putting, more energy in to dissipate the energy that is already in the water. So it seems problematic, and we are standing in front of large investments, not just in Metro, but in other urban areas here in Colorado as well. Colorado is one of the first states in the country that is implementing these temperature standards. There are other states which are looking at temperatures along the Rocky Mountains, because that's where we typically have cold water streams. The regulators go a little bit differently about how they are implementing and enforcing these standards. Colorado, I would say, is the most stringent, and that's why we talk a lot about what we want to do with this heat in our state. So let's talk a little bit about thermal energy. When you look at wastewater, there is energy in there in different forms, right? So we're pulling biogas out. I said that earlier, that biomass comes originally from organic material that is in wastewater, and we're quite efficient to remove that organic energy and transforming it into biogas and other energy forms. That what we call here chemical energy is a small portion, and that is relatively well recovered by at least larger facilities that are producing biogas. The far greater portion of energy in wastewater is thermal energy, and so it behooves us to think about how we recover that and how we make it useful again. There is a projection just from Department of Energy looking for North America. It's quite a lot amount of energy. And so the industry has started in Europe already since about 20 years, and in the US now since about 10 years, to look further into how can we recover that energy. The actual mechanics of recovering that energy there is nothing new. If you look at that picture, you see the sewer lines. So sewer lines are the big pipelines that are running under the ground that are transporting the wastewater to our treatment facilities. And so tapping into that sewer line and bringing that water up is one opportunity. You run it through a heat exchanger. Yes, we're talking about low-grade heat. I showed you that bandwidth between the minimum and maximum temperature is relatively small, but the heat exchangers can amplify either for heating or cooling, and then that can be run either in a heat loop or in an ambient loop into buildings where that is recovered and transformed into heating or cooling for those buildings. So that's the principle of it, and there's nothing new about heat exchangers or heat pumps. We have used them, and you're coming to this event far often than I do. I learned a lot about heat pumps and their efficiency because we have them now in our home and not using natural gas anymore, and it's quite impressive how efficient these heat pumps are, and even if you're going outside and freezing, you still get your home heated up. So quite impressive how this technology has advanced and how efficient it has become. Here's a schematic about what we call a district energy schematic. Who is not familiar with district energy systems or had not heard about that? Okay, so a district energy system is interesting in this context because it's essentially a combination of buildings or houses where we're providing in a centralized plant, a utility plant, a heat exchanger to provide heat for a larger group of buildings. And that makes it more cost effective than going into each individual residential area and putting these systems in. Because for wastewater, heat recovery and thermal energy from wastewater, the systems become expensive. We need to bring that water out of the sewer line, and so that's pumping involved, and we need to clean it and screen it so that we're not blinding the heat exchangers. That's really the majority of the cost is right there. Probably about 80% of the cost is right in that infrastructure. The actual heat exchangers, there's not as much to it in comparison. So doing this type of treatment for a larger area becomes way more cost effective, which is why for the large opportunities that I'm talking about at the end, I show you some mid-sized facilities as well, but for the large amounts, we need to start thinking about where we can use that heat and where is it cost effective to use that heat. And that is typically when we have new construction, and when we have commercial scale or multi-family unit systems where we can use that. This is just a schematic to explain the components of a heat pump. Every refrigerator has these systems. They consist of a condenser, an expansion valve, an evaporator, and a compressor. So it's thermodynamic system that we have used already in HVAC systems, in refrigerators. And we can run these heat pumps in one way or reverse them. That's nice. You can use the same infrastructure for heating and for cooling, which makes these systems also much more cost effective. I want to show you a few systems that are currently on the market that are being used. So we can use heat exchangers that are directly inserted in the collection system. These systems are currently provided through the European market because in Europe, as I said, the energy is more expensive. And companies have started to look into that already about, I would say, 10, 15 years ago, where systematically larger metropolitan areas like Stuttgart, Augsburg, Berlin, they look very systematically at their collection system and analyze where are developings, an IKEA goes in here, can that be tied to a collection system, and are implementing very systematically these types of systems. So some of these technologies are coming from Europe and are marketed now here. But there are also companies, I'll show you, that are developing out of the United States. So this is a system where the heat exchanger is implanted in the collection system with a working fluid that is brought outside to a heat pump. And typically we're trying to keep the buildings close in vicinity to the sewer lines in which we are tapping into, just because you get heat loss. With ambient loops specifically, you want to be closer because the temperature delta, I show you that in the next slide, is not as large. So we want to be quite close to the buildings. For hot water district energy systems, we can pump it quite a ways. I'll show you that for this for City of Vienna, for example. This is another system, Shark Energy system. We actually have two systems of these in Colorado. I'll show you that later. One in Boulder, relatively new, about a year, taken in operation. There in the Boulder Commons, if you're familiar with that new mixed-use building in Boulder, and then also in one of our large facilities we have at the Denver Western Stock Show, National Western Stock Show. I'll show you that later on. So that's from Shark. This is a system that actually pumps out of the sewer line, the wastewater. It's being pumped out, brought into a screening system, and then into a heat exchanger system, and then from there it pipes into a district energy system, or it can heat a single building. And this is the last one, the last type. Huber is a distributor of their technology here in the US and in Europe. So these are systems which are essentially standalone. You see here the system where, again, water is pumped into that system, and the size of it is probably, something like this, this, and this. So it fits into parking lots, it fits into basements of larger commercial areas or public buildings, and provides heat into the heat and cooling system. We have now also systems that we can put into channels, which may be interesting for Metro. I explain that in a little bit. So there's different combinations now, and I want to emphasize that there are competitors on the market. That's always good if you find competitors that are providing this, because then the development of the technology is gaining footage in North America. So I want to talk about the first projects we have here in Colorado, and hopefully you find a time, if you're interested, to actually see those installations. So the National Western Center is located, as you know, the stock show. Has been a lot of redevelopment, and as part of that redevelopment, a portion of the area was used for the Spur campus. Is anybody familiar with the Spur campus? Okay, so this is actually a very cool area. If you haven't been there, it's also architecturally really interesting. But since you're scientifically interested, the Spur campus is organized and administered by the Colorado State University. And there are 4 buildings right now. It will be expanded in the future, but there is a hydro building. I have a photo for this. I think a livestock, agriculture, and a 4th one, maybe, I think a medical building, right? Health, yes. Yeah. And so this development, these are quite sizable buildings where research is taking place. Students are there, but they're also providing public events. These buildings are provided with heating and cooling through one of our interceptor, the Calgary interceptor that you see here. So this is actually the interceptor, how it was routed before that development took place. There were 2 reasons to tap into that interceptor. First off, it was really in the way. It didn't look very nice. When you go to that place right now, that interceptor has disappeared. It's now underground. We paid for that. We got it underground, and that really opens that area up. And it's now very nice and attractive to be next to the South Platte River. So that was aesthetics. Yeah, very well. An interceptor is just a large collection, a large part of the collection system. So a number of the sewer pipelines of smaller diameter feed into a very large interceptor. I'll show you a map later on. And we have several interceptors that come from different areas of the metro area into our facility. So the most important thing about it is size. It's a 78-inch interceptor, carries a lot of the water, has very consistent water. And so that was also opportune to tap into that interceptor to extract heating and cooling for that new campus. It will be expanded in the future as the Western Stock Show continues with its development. Currently there's the capacity of that system is 4 megawatts that we are providing heating and cooling for those Spur buildings. Here's a schematic of that, very similar to what I showed you before. City of Denver, and our City of Denver for that interceptor is providing wastewater. It contains heat. We have a wet well from which we are pumping the wastewater into a filter. It goes into a heat exchanger. The system is from shocks that I showed you before. And then that heat is put into a ambient heat loop, which carries in summertime cooler wastewater, which is used in these 4 different buildings for cooling of the buildings. And in wintertime, we're providing hotter water in the ambient heat loop that is then used in additional heat exchangers in each of these buildings to provide heat for those buildings. Here are some statistics on that for cooling. Overall, we have in the capacity of that system about 30 megawatt. Currently, we're not using that all because it's not yet built out. And we're providing heating for that in winter. There is for those of you interested in the mechanical portion of that, we're providing about 80-90% of the heating and cooling of the system. There is a redundant heating and cooling system that is typically not in operation when our system is operation, but that's just required to provide heat and as a redundant unit for that. All right, so here you see a photo of the Spur campus. This is the hydro building. We're working with the CSU campus in that building together on other projects because they're also focused on wastewater and water research and treatment. So there's a lot of water-related innovative work that goes on in there. But we are saving with that system quite a bit of CO2 emissions. It's estimated that at our current energy portfolio that we have here, the 4 megawatt and the actual power use of that is reducing about 2,600 tons of CO2 per year. We are reducing so these heat pumps, when you bring wastewater in, can reduce the temperature of the water up to 5 degrees Celsius. And then, of course, that water is mixed and blended again with the rest of the water, so we don't see that in our facility. The impact on our facility is about half a degree. I told you we need about 7 degrees, so we have a ways to go, and we need to look at larger installations to really make use of that larger energy and offset the construction of cooling towers substantially. We also have a smaller system. This is actually on the wastewater treatment plant campus. So our treatment facility at Denver, and this is OSCB, we call it the operations building. This is actually, my office is in this window. This is actually where my team is working, our innovation team, and we constructed that building a couple of years ago because we needed to expand. And that building is provided with heating and cooling from our wastewater. It's a very similar system where we are having a pump. We're going into the north secondary effluent vault, so that's treated wastewater. We bring that water to a heat pump and are feeding it into our building. So this was relatively easy because it's a new construction and those systems are cost effective, and I'll show you later on some economic data on that, but it's cost competitive and has ROIs that are actually quite attractive. We are currently working with Xcel and the City of County of Denver on a pilot study that is in planning. Xcel is being asked to look at ways to decarbonize their energy portfolio for heating and cooling for downtown. There is a district energy system infrastructure already in Denver, which is opportune because we have a lot of the underground facilities already that are currently being used and being fed through the Denver steam plant and cooling from Xcel. And so the City of County of Denver is leading a project in partnership with Xcel, and we are partners in that as well because we have a interceptor that is running very close to the downtown area where that heat loop is, and are evaluating if we can use the heat recovery system that I showed you earlier, implementation of these heat exchangers right into that interceptor, and feed a portion of that future renewable portfolio of energy that should feed that district energy system from our interceptor. So it will provide a portion of it, or it can provide a portion of it, not everything, but there are other heat sources that they are looking at, geothermal, etc. So conditions that favor district energy systems are, you want to be in the vicinity of a interceptor or a larger sewer pipe. So we have all of these, of course, mapped and are in the process to monitor very strategically the temperature profiles in these so that when there is development in anywhere in our service area that we become aware of, we can essentially go to these maps and work with engineers, with architects and developers together to identify what heat is available and provide and facilitate the engineering evaluation of is it feasible to provide heating and cooling for new buildings from our interceptor. And we do get requests 2-3 times a year where people are starting to become interested because at this point in time it is free energy and there are ROIs associated with it. You don't really have ROIs if you continue with natural gas because you continuously pay for that. And it is, so this is interesting because we have still relatively a good amount of space in Denver, but if you look at very tightly developed areas, for example, New York City or Vancouver, those are areas and cities that have climate goals, right, for decarbonization of their systems and for heating, for their building infrastructure as well, as does Denver. But specifically in these very urban areas, you don't have a lot of alternatives for renewable energy. You don't have the space on these buildings to put solar. Solar on a very high, five-floor building may only provide you a fraction of what your energy demand is. It's difficult to put wind in. That happens usually way out in the plains. So mining into the sewer for heating and cooling is actually a very attractive way because that energy is very local and is right there. In some areas where this development has already been going on, if you look, for example, in cities like Berlin in Germany, they actually do need now to manage how many of the of customers on their sewer lines they are allowing, because you do not want that upstream users of heat affect contracts, established contracts with downstream users. I hope we have this problem very soon in our area, because it shows that there is actually demand for it and competition for that energy. So a little bit on international developments. This is a type of energy mining that has really taken off in some areas faster than here. We're working on it, and that's why I really appreciate the opportunity to talk with people that are working in the space and are interested in energy about this, because we need to just be more aware of this. Vancouver has some very large district energy systems already in place, and that is driven, not even in any of these areas, is this driven by the demand that people are required to cool the effluent. This is actually a double down in our area, that we have utilities who will need to pay millions. Our estimate for cooling towers is 100 million. So we need to put that money anyway on the table, not to speak of the additional operational costs that will be probably also in the hundred thousands for energy each year. So not only do we need to put that cost in these areas in which these energy systems are taking off is for economic reasons, because it's a competitive energy source, and for environmental reasons, because all of these areas are trying to decarbonize, and it's very difficult to decarbonize the building infrastructure that we have. So interesting, if you're going to Vancouver, very interesting large district energy systems there. The same in Berlin, a number of them. In fact, every year they have about 2 or 3 new systems that they bring online, as do other cities across the globe. If you're interested in that, there is an interesting study from the Water Research Foundation that analyze these systems and trends. I want to point out a couple of things here in Colorado specifically. I mentioned the Boulder Commons, the Avon wastewater treatment plant. If you're a skier, you may be there. If you're going to the public pool next to Avon, that is actually being fed by heat from the effluent in Avon from the wastewater treatment plant. The National Western Center, I showed you that earlier, is one of the largest installations we have in the US today. And then there are other ones. The interesting thing in, for example, some of the East Coast states, DC Water, so that's in Washington, D.C., the large utility. They negotiated with states to get thermal RECs. Is anybody familiar with renewable energy credits? Okay, we get those for solar here, right, for wind power. And so if you have a solar system, you own the RECs on that system. The DC Water negotiated with state regulators that there would also be a market for thermal RECs. Some states have that for geothermal, but they put in that geothermal also can include heat from sewer systems. And so DC Water is actually making some good money with that, several hundred thousands a year, that they reinvest into the next installation of these systems. So usually utilities are not in the business to really make money out of that, but it is a smart business move, because as we're wanting to expand these systems, it is helpful to make some economic profit with that can be then reinvested. So if you're ever in DC, they build a new administrative building, and that administrative building sits right on top of one of their effluent pump stations, and so it's very easy for them to mine that energy for heating and cooling of their system. This was really interesting. I mentioned that earlier. We visited that facility in Vienna because it's very large scale and about the scale that we would need here in Denver to find a use and a market for the about 100 megawatt plus that we need. City of Vienna is interesting because it has a district energy system underlying the whole city. For a heat loop and a separate cold water loop. So they are bringing through these heat exchangers the temperature up to almost boiling, I think 95 degrees Celsius or something close to that, and send it for miles through the city together with other heat sources, renewable heat sources for their city. Their goal is by 2040 to decarbonize their energy systems citywide. And they invest really in large facilities to make that work. So the technology is there. I wanted to show you this. This is a summary I did some years ago just for a couple of these installations that I mentioned here, where we investigated the capacity but also the payback periods. And so payback for these systems lays about at the minimum at about 5 years. But somewhere between 5 and 10 years if it's a new construction and a larger commercial scale. So very attractive, even in comparison to solar or other energy sources, geothermal. So finally, I want to, this is the last section here, talk about the energy recovery opportunities. So this is a map that's relatively small, but we also have that available on our webpage where you see larger interceptors that we are responsible for. There are pipelines that feed into these interceptors that the city and county of Denver may be responsible for, or our connectors. So there are other maps available, but these are just the ones that we are responsible for. So if we get a request, for example, from Mile High or larger developments, or the ball arena will be in the future be modeled, that's where we can go into these maps and show what are the flows, how much energy can be pulled out, can that be sufficient to match the demand of these new developments. There is an opportunity for large demand. We are relatively close to the Cherokee power station, so if you're going on that bike path or you're driving down York Street, on one side is the Cherokee power station, and right on the other side of York Street is our facility. And so we have underground facilities already that go from Cherokee over into the Denver area. And so it will be an interesting engineering study that we will commission soon, where we look at conceptually what would be required for us to build infrastructure, bring that heat over to Cherokee, feed it into that downtown area. Is that feasible? How much would that cost? And these are really, when I mentioned early on, we need partners of that. This is not typically the business that wastewater facilities are in. We are getting into that business because we, want to make use of the energy that we have, just like we're using other resources that are in our wastewater, but also because we have a very urgent permit driver. We can either invest in the next years massively into cooling towers, or we can use the years to promote and find opportunities and at least assess the feasibility of opportunities to use that heat in small developments in the metro area, but also at a larger scale. We have, from the policy side, a good framework here in Colorado and in Denver because the policy opinion and is currently with a number of these policies that are set very attractive for decarbonization. Excel has a clear plan and a demand to decarbonize their energy provided, the energy that they are providing. They're making very good progress on electricity and the electricity portfolio, but it's challenging to decarbonize the natural gas system. And that is one opportunity where a technology like that can help to substitute quite the amount of heat and cooling that we are currently providing through natural gas in these buildings. So challenges to overcome, just to summarize, and if any of you have work in that space, work with developers, work on the building side, it is useful to make architects and developers aware of this, and mechanical engineers who are working in this space, because many are not familiar with this, and some are working on larger commercial scale, residential or commercial buildings, and it's just one form of energy that is technologically mature. And is often just a question of that being aware of that and evaluating whether the location, the sizing of the system, etc., is opportune and can be provided through wastewater. And then we are always looking for opportunities to talk, make people aware of it, so that we also create opportunities and awareness for larger scale systems that we may, in partnership, engineering-wise and from an economical side, evaluate. And that was it. Thank you very much for your attention.
I know you're doing, capturing heat before it gets to the plant, and then looks like you're gonna, on the outflow, you're gonna maybe take some of that heat, put it to Cherokee and put into the district heating.
We need to evaluate whether that's feasible. We're not doing it right now.
Right, yes. But I was wondering, on the outflow, is why not use an ammonia or some other refrigerant, take heat out of the outflow, run a turbine. Theoretically, you could, out of that 150 megawatt thermal, you could get 50 megawatt electrical. And that would that'd take 1/3 of the energy right out of there, right, and generate electricity. You got your customer right there, your own electrical customer. And I wonder if they're looking into some kind of ammonia or other refrigerant cycle to run a turbine because a turbine converts heat to mechanical energy and get electrical energy from the generator and do that.
I'm aware that you can use heat also to convert it to electricity. My knowledge was that it is way more costly. But you're right, it should be something we're looking at, especially since we otherwise need to invest anyway in these systems. So, yeah, thank you.
Hi, I was wondering, I guess first, does the Denver area have a combined storm drain system and sewer?
We have a separate system.
Oh, they're separate,
We're not
okay.
a combined sewer system.
I was going to ask if that rain events have an effect, how much they affect the temperature.
I mean, we have
sewer.
some areas in our system that have what we call I&I, infiltration and inflow. It's unintentional, but it's because, some areas of the Denver metro sewer system are old. So we get some storm events. Our peaking factor, which means when it rains, the flows we get to the typical dry weather are relatively low. And that helps because for the temperature profile in the system, it's very stable and fairly predictable. So what I showed you there is fairly predictable also in areas of our collection system.
Thank you.
Hi, Tanja. Great presentation. What is preventing Denver from becoming Vienna with the systems they have? Is it strictly money, or are there other challenges?
I think we have just not looked at it yet. I think the attention, if you go in any of these policies or guidances for, Renew Denver or energy below our feet, most of them talk about geothermal, but rarely is even wastewater mentioned in there. And so I think the awareness is not yet there. And we also need the economic studies that we probably will initiate, and our agency, our district will initiate, because we need that information. And so I think there is a couple of things that make Vienna, I think it's not a surprise that Vienna is having that and we not yet. First off, I mentioned the awareness in Europe, these systems have been constructed longer. The technology has been longer around, and so, people know, oh, Berlin is doing this, we should look at this. Vienna specifically also, the energy system, the solid waste system, and the wastewater treatment system, all of these utilities are under the city of Vienna. It is easier to have these negotiations. I can tell you, we tried for a long time to talk to Excel and even get the relationships to talk about these and talk to the people who can make strategic decisions about this. It's not as easy as if it's all under the umbrella of one city, I don't know, government or administration. So also that they have the power system right there, just the whole logistical evaluation and making it all work was a big advantage we heard from them when we visited them. So we have here some logistical issues just to get these partnerships going, get the engineering evaluation done. I think if an engineering evaluation showed there is a business case to be made, that I think it is possible to get the funding ultimately to doing it. We just need to get the evaluation done and make the business case for it.
In Vienna or Berlin, they've had district heating systems for 100 years. So it's really plausible and comparatively easy to move into energy recovery if you're starting from that basis.
Yeah, the underground infrastructure is more commonly available in cities in Europe, that's true. There is a trend towards district energy in North America now. If you're tracking what happens in the northwestern part of the US and in Canada, around Vancouver and in other Canadian cities, there are requirements for new construction, for example, to tie into district energy systems and to decarbonize district energy systems. So there's a trend towards that, yeah.
And one question related to that is how easy is it for these engineering companies in, say, Austria or Germany to create a system that will work in the United States or in Denver specifically? Is that...
You mean, for example, Huber to bring their system here?
Mm-hmm. Yeah.
You know, it's not the technology that's the challenge. Their wastewater is very similar. We're talking, it's maybe even more concentrated in Europe because they're using less water. So the technology is less the problem than the business arrangement. So it's interesting, for example, Huber, who has the technology in Europe and has a lot of business over there with these types of systems, needed to partner with Noventa, which is an energy company, here in North America to even get into a business. So Noventa figured out a business arrangement with a large hospital in Toronto to even make the energy contract and get the economics to work. And then Huber essentially provided, for the engineering side, the technology is the easy part. The arrangements, if I showed you, for example, for the National Western Center, the arrangements of partnerships, it's very nestled. Who does what? The arrangements and partnerships are the challenge.
You had a pretty sobering remark in there, which was basically that, if I remember correctly, you're at 1 and you need to get to 7. I forgot what the units were.
Degrees Celsius reduction in the temperature.
Can you talk a little bit more about the prospect for reaching that goal and when you might reach it and what it might require?
Well, there are a few moving parts to that. Right now, as it stands, the discharge permit for our facility, for the large facility, requires us to meet these temperature limits by 2031. We will not meet those. It's challenging. There's reasons for that, and we made regulators aware of this. So that's a challenging situation. So we already somewhat need to think about what we're doing with that time, and we're taking a two-pronged approach. We're testing Cooling towers, because we need to know whether they work. And in a plan B, we are evaluating the opportunities and large-scale opportunities for doing an alternative, a recovery approach. For our second facility, which is smaller, our timeline is even shorter. So there we need to comply in 26. We are, I think with that, 26. So in 2 years, we need to comply. That is a smaller facility and treats less than 10% of the flow of the larger. It's the Brighton area, etc. For that facility, we are building cooling towers. So we just decided, we put the money in. It's still expensive. I think our current cost estimate is somewhere around 15 million that we need to put in, and that is not even yet for the full capacity of the system. It's still a demonstration scale, but we put that in and are trying to comply by that date. There are a few...
A question about compliance. Are there only sticks or are there also carrots? I mean, you mentioned that...
Only sticks. Only sticks.
That you would be facing fines if you're in non-attainment?
Yeah, I mean, it's the reality. If you have a permit limit and you have permit limits in there and it's effective and you're violating, then, yeah, I mean, you're describing the reasons why you're violating, but if it's negligence and it accumulates, there are fines associated with that, yeah. In parallel, the situation on the regulatory side is right now a little in flux in Colorado because regulators recognize that we have, I'm just talking about temperature. There are about 2 or 3 other more parameters where we are ratcheting down quite substantially the treatment requirements for discharge. And so this is just one of the issues we're actually dealing with. So regulators do recognize that there is a lot coming and a lot that utilities would need to pay and prepare for, and where we don't have technologies yet even in some areas. And so there is right now a discussion with regulators and the Water Quality Control Commission, so a process to evaluate what is actually feasible. Right now, temperature is not the highest priority. It's right now the highest priorities are nutrients, to find a solution for nutrients in our area. But there is an awareness that temperature creates challenges. And so we don't know yet as permittees where that goes. We need to plan for what we have currently in place. And so, long story short, we have some years. I do think it makes sense to look at opportunities and use these years to put those into place and show, at least when we go into renegotiation of our permit, which should occur at the end of this decade, if we can show, hey, we made some progress and we have potential and funding to substantially reduce our temperature through other means, that can be part of a negotiation strategy.
Still on the topic of, I guess, regulation, do other locations in Colorado outside of Denver have different standards based off of, I guess, Colorado regulations? So say Colorado Springs, do they have a different temperature that they need to hit? Or Pueblo or something?
So in my previous work, before I worked with Metro, I worked as an advisor, as a consultant with many utilities in Colorado. I have not worked for Colorado Springs on temperature, but here's how you can figure this out. Generally, we have 3 major types of water bodies. We have cold water, and we have warm water 1 and warm water 2. And in Regulation 31 and the associated regulations that are, that would be, I think, Fountain Creek, or I don't know exactly where they are discharging to. In these regulations, for every segment that any discharger discharges into, there are stream segments. By finding out that stream segment, there are tables, and these tables have all the water quality standards, and the temperature standards will be in there. And so I do not know right now exactly what Colorado Springs situation is. Generally, I mean, we have almost every large urban center from Fort Collins down to Pueblo is impacted by that. Some only need to remove it by 0.5 degrees Celsius because they have a lot of dilution, and others, metro and CRES, are actually about the worst affected.
I guess my other question is kind of related, but in, say, these smaller cities, you'd probably have much more area to start and operate like these heat removal systems, right? But what is sort of the population breaking point or threshold you would need to even consider it for return on investment or something?
So you mean cooling towers or heat recovery systems?
Oh, heat recovery.
Heat recovery systems. So, I showed you this one table where I put a couple of different sizes of systems on. So take, for example, Boulder Commons. Boulder Commons is so I would say single family, no way, not effective. It starts to become cost effective if you have multi-family units. And some areas plan several multifamily units next to each other. And for those systems, it starts to make sense if you have a centralized CUP and you're providing a sort of commercial scale or multifamily unit, these technologies. For commercial facilities, it becomes, if you have office buildings, it becomes cost effective. We have systems for hotels, for hospitals, for schools. So it is less the size of the community, but more the size of the system, of your building system. And those are sort of these decentralized units that you can put into the basement of these buildings. I will say, and that maybe that's where you're going, that for the effluent side of a treatment facility, those systems make a blip. You may not measure that. And in fact, we cannot. So for some areas, for example, we made a study about Boulder. For Boulder, it could work. They have about 2 degrees, and if they actually were systematic and using all of the potential, they could meet that temperature objective through in the sewer shed through heat recovery. For metro, we have the problem. So a big part of our treatment is biological, and for the biology to work, we need some heat. If we took that heat out to 7 degrees in just the sewer shed, so upstream of our treatment, we would actually lose a lot of capacity. The biology will still work, but it works much slower, which means we would need to provide more area for that same treatment. So we call that derating of the capacity. That's why we are also looking now at effluent and at larger scale systems at the effluent, because it's downstream of that treatment.
Yeah, and I just wanted to interject one interesting point about the whole water energy nexus. Something that is happening more and more due to climate change and elevated temperatures is that thermal power plants, be they nuclear or coal burning plants or gas plants, which rely on cooling towers or on river water, have to ramp down or even shut down when the temperature of the river is too high. And we've had more and more incidents of that, where exactly when we need the power the most, in the summer when everybody cranks up their AC units in order to stay alive, that's when we have to ramp down those power plants. And one of the reasons is fish kill. Fish have evolved to survive a particular water temperature, and if it goes above that, they often have nowhere to go and they die. I've actually been at Lake Constance, where I'm from, on the Swiss-German border, where swimming in the lake during a heat wave that lasted 6 weeks or longer was no longer a pleasure, because there were dead eels everywhere along the beach. The stench was overwhelming. Not fun anymore. So that little bit about the water energy nexus and now the beer conversation nexus. I want you all to give Tanja a round of applause and then rejoin everybody in the comments and eat something, drink something, and talk to each other. Thank you very much.
Thank you.